Welcome all. I am AMALORPAVADOSS presenting a lecture on aromaticity. There is another method for arranging the pi molecular orbitals in the increasing order of energy, and that was proposed by A. Frost in 1953. He proposed a procedure for arranging the pi molecular orbitals in the increasing order of their energy and for the distribution of electrons in those orbitals. According to his procedure, we have to draw a circle first. Draw a circle, place your cyclic system, the polygon, within the circle in such a way one of its vertices is touching exactly the bottom of the circle and all other atoms of the ring are touching the circle. Fill these molecular orbitals with the electrons according to Aufbau principle and Hund's rule. Now, so we have done three steps now. Draw a circle, place the cyclic molecule within the circle in such a way one of its vertices is touching the bottom of the circle and all other vertices are also touching the circle, and then fill the molecular orbitals with the electrons based on Aufbau principle and Hund's rule. And now bisect the circle into two equal halves horizontally. All the molecular orbitals which are lying below this horizontal bisecting line are called as bonding molecular orbitals, and those pi molecular orbitals which are above this horizontal line are called anti-bonding molecular orbitals. Now let us try to apply the procedure proposed by Frost for various systems. Let us take this cyclobutadiene. This molecule, first of all we have to draw a circle and we have to place this cyclic molecule within the circle in such a way one of its vertices, that is one of its corners, is touching exactly the bottom of the circle. At the same time, all other atoms of the ring should also be touching the circle. So now we have placed the cyclobutadiene within the circle, and now wherever the atoms of the ring are touching the circle, you draw lines. So here the molecule is touching here, you draw a line. Here it is touching, draw a line here and here. So wherever the atoms of the ring are touching the circle, you draw a line, and all these lines are representing the pi molecular orbitals. And now this is the increasing order of energy. When you go from bottom to top, you are going from lowermost energy to highermost energy. Therefore, in case of cyclobutadiene, there are four molecular orbitals. And now you have to bisect the circle into two equal halves horizontally. All the molecular orbitals which are lying below this line are called bonding molecular orbitals. Therefore, for cyclobutadiene there is one bonding molecular orbital, and all molecular orbitals which are above this horizontal line are called anti-bonding molecular orbital. Therefore, it has one anti-bonding molecular orbital. If any orbital is lying on the horizontal line itself, they are called non-bonding orbitals. These are the molecular orbitals with the energy equal to that of the atomic orbitals. Now, there are four electrons, delocalized pi electrons in cyclobutadiene. We have to fill them in the molecular orbitals. There are four molecular orbitals, one with the lowest energy, one with the highest energy. There are two non-bonding molecular orbitals. Now 2 electrons should be filled here, and the remaining 2 electrons will occupy these 2 orbitals according to Hund's rule. Therefore, this cyclobutadiene in its pi molecular orbitals is having 2 unpaired electrons. Therefore, it is an anti-aromatic system. Let us consider cyclopentadienyl anion. We have to apply the Frost procedure now. Draw a circle, place this structure ring within the circle in such a way one of its vertices is touching exactly the bottom of the circle, and now wherever the atoms of the ring are touching the circle, you draw lines, and all these lines are representing the pi molecular orbitals, and their energy will increase from bottom to top. So this is the bottommost molecular orbital with the lowest energy. These are the topmost molecular orbitals with the highest energy. So when you go from bottom to top, the energy increases. Now you have to bisect the circle horizontally into 2 equal halves. Now you are bisecting it with a line, and all the molecular orbitals which are lying below the line are called bonding pi molecular orbitals. Those which are lying above are called anti-bonding pi molecular orbitals. Now in cyclopentadienyl anion, there are 2 pi bonds with 4 electrons, and this carbanion is having a p orbital with a pair of electrons. So 2 electrons are here. So totally there are 6 electrons, and all these 6 electrons have to be distributed in these molecular orbitals now. So 2 electrons will occupy the orbital with the lowest energy. The third electron will go here. Fourth electron will go to the next pi molecular orbital. So these two have to be singly filled first. Then the fifth electron will go here for pairing. Sixth electron will enter here. Now all the 6 electrons are distributed in the bonding pi molecular orbitals itself. Therefore, all the bonding pi molecular orbitals are completely filled, and hence this system is extraordinarily stable, and we call this system as aromatic system. Therefore, cyclopentadienyl anion is aromatic. Let us consider benzene. We shall apply the Frost procedure here. Draw a circle, place this hexagon, the benzene molecule, within the circle in such a way one of its vertices is touching the bottom of the circle. At the same time, all other atoms of the ring are also touching the ring. Now bisect the circle into 2 equal halves horizontally with a line here. All those molecular orbitals which are lying below this line are called bonding molecular orbitals, and those above are called anti-bonding molecular orbitals. Benzene has 6 pi electrons. Those 6 pi electrons are occupying the 3 bonding molecular orbitals as shown here. Therefore, all the bonding molecular orbitals are completely filled, and there is no electron in the anti-bonding level. That is why this system is also extraordinarily stable, and hence we call it aromatic. We shall apply the Frost procedure for these two systems now. This is cycloheptatrienyl cation. We call it tropylium ion. This has 3 conjugated pi bonds with 6 pi electrons, and here we have a carbocation with an empty p orbital. So totally this pi bond is made with 2 p orbitals, and this pi bond with 2 more p orbitals. Here you have 2 p orbitals, here an empty p orbital. Totally there are 7 p orbitals present in this system. All these 7p orbitals can make 7 pi molecular orbitals. Now, you apply the Frost procedure for this system. Draw a circle, place this structure, place this ring within the circle so that one of its vertices is touching exactly the bottom. At the same time, all other atoms of the ring are also touching the circle. Wherever the atoms of the ring are touching the circle, draw lines, and these lines are representing the pi molecular orbitals. Now bisect the circle into two equal halves horizontally. Now all those molecular orbitals which are below this horizontal line are called bonding pi molecular orbitals, and these four are called anti-bonding pi molecular orbitals. Now in all these 7p orbitals we find only 6 pi electrons, and all these 6 pi electrons will occupy these bonding molecular orbitals. So these bonding molecular orbitals are completely filled, and hence this system is aromatic. Let us move on to the next system, that is cyclooctatetraene. This has 4 pi bonds which are made with 8p orbitals. All these 8p orbitals can interact with each other to make 8 pi molecular orbitals. Now we shall apply the Frost procedure for this system. Draw a circle, place the structure inside in such a way one of its corners is touching the bottom. At the same time, all other ring atoms are also touching the circle. Now bisect the circle into two equal halves. Those orbitals which are lying below are bonding, and these above are anti-bonding, and those who are lying on the line are called non-bonding molecular orbitals. Now we have to fill these 8 pi electrons in these molecular orbitals. So as usual we will fill 2 electrons here, third one here, fourth one here, then fifth, sixth here, seventh electron and eighth electron here. Now in this arrangement we find there are 2 unpaired electrons. So the presence of 2 unpaired electrons should make this system to behave as a diradical, an extraordinarily unstable, extraordinarily reactive, anti-aromatic species. So we expect this system to be anti-aromatic, but we find this molecule being non-aromatic because this molecule is non-planar. So we have seen, for a molecule to be aromatic or anti-aromatic, first of all it has to be cyclic and then it has to be planar. So but this molecule is non-planar. So we will discuss about this structure later. Polygon rule. This polygon rule also, just like the Frost procedure, this polygon rule also speaks about how to arrange the pi molecular orbitals in the increasing order of their energy. And according to this polygon rule, the energy diagram of an aniline has the same shape as the cyclic compound itself, with one vertex at the bottom. So in case of this structure, a hexagon, there should be 6 pi molecular orbitals, and those 6 pi molecular orbitals will have their increasing order of energy as shown in this picture. Therefore, from all our discussions, we come to know that aromatic molecules are cyclic, planar, and they have completely conjugated or completely delocalized pi electrons, and the number of delocalized pi electrons is equal to 4n plus 2. And in case of anti-aromatic molecules, they obey the first three conditions, that is they are cyclic, they are planar, and their pi electrons are completely delocalized all over the ring, and they differ only in the fourth condition, that is the number of delocalized pi electrons is equal to 4n. And all those systems which are not coming under these two categories are called as non-aromatic systems. So a compound that lacks any one of these three criteria, if it is acyclic, if it is non-planar, and if it is not having completely delocalized pi electrons, then such a molecule is called non-aromatic molecule. Therefore, the non-aromatic molecules are the molecules which do not obey any one of the first three conditions. The stability order of organic molecules is given here. The aromatic molecules are the most stable, and these aromatic molecules are more stable than the non-aromatic systems, and these non-aromatic systems are more stable than anti-aromatic systems. So the anti-aromatic systems are the least stable systems. So an aromatic compound is usually more stable than a similar acyclic compound having the same number of pi electrons. Benzene is an aromatic compound and it is more stable than a similar acyclic system. So benzene has 6 carbon atoms, this also has 6 carbon atoms. Benzene has 3 conjugated pi bonds, 135 hexatriene also has 3 conjugated pi bonds. But this benzene, an aromatic molecule, is more stable than a similar cyclic compound having the same number of pi electrons. And an anti-aromatic system, an anti-aromatic molecule or ion, an anti-aromatic system in general are less stable than the acyclic system with the same number of pi electrons. Here we have cyclobutadiene, an anti-aromatic system, and this is less stable than an acyclic compound having the same number of 4 delocalized pi electrons. And this cyclobutadiene anti-aromatic system is found to be less stable than this 1,3-butadiene. And in case of non-aromatic cyclic molecule and its open chain counterpart, they have almost similar stability.